I'm going to show why in an isosceles triangle, the perpendicular bisector of the base passes through the vertex of the triangle. This property of isosceles triangles will come in very handy in future videos when I attempt to prove the properties on other shapes. We'll begin with two horizontal lines. I'm going to intersect both of these lines with a dotted perpendicular line. On the left, you should be able to see that the perpendicular splits the horizontal line into two unequal parts. I'm going to give those two parts the values of A and B. The longer side is A and the shorter side is B. Now if you look at the right hand side horizontal line, I've set things up so that the perpendicular splits the line exactly into two equal parts. And I give those two equal lengths the label of C. I'll emphasize the tops of both of the perpendicular lines. And now from the end of each line, I'm going to draw two lines that meet at the top of the intersecting perpendicular. We'll begin with the structure on the left, and you can see that this creates a triangle where the vertex is at the top of the perpendicular. We'll repeat this for the structure on the right hand side. Again, a triangle is created where the vertex is at the top of the perpendicular. The height of a triangle can be given by the length of the line that travels from the vertex of the triangle to the base that's perpendicular to the base. So for both triangles, I'm going to give the length of the perpendicular that's inside the triangle the value of h. For our purposes, we don't need to distinguish between the two triangle heights, so I'll call them both h. The first thing I want to do before examining these two triangles and drawing conclusions about them is to determine the lengths of the sides of both of the triangles by using the information we already have, that is the split bases and the heights of each triangle. First of all, notice that the perpendicular has split the main triangles into two more triangles. The two triangles that result from using the perpendicular share the same inner edge, which is the perpendicular. But because this dotted line is perpendicular to the base, the angle between it and the base must be 90 degrees, which means that the triangles which were created as a result of the perpendicular must be right angle triangles. Let's put those right angles in. And for each of the four resulting triangles, we already have two edge values, the height and the base for each triangle, which means that we can use those values to get the length of the third edge of each triangle. We know by Pythagoras that in a right angle triangle, if you take the sum of squares of the edges that are adjacent to the right angle, that will give you the square of the edge that's opposite the right angle, which is the hypotenuse. And we can use that principle to calculate the length of the hypotenuse of each of these four smaller triangles. Let's give each of the four edges their own unique label. We'll call this one W, this one X, this one Y, and this one Z. In the first triangle, the edges that are adjacent to the right angle are A and H, so that means that A squared plus H squared must be equal to W squared. And on the right hand side, let's put the X first. X squared must be equal to B squared plus H squared. And Y squared, that must be equal to, well, the edges adjacent to the right angle are C and H, which means that Y squared is C squared plus H squared. But the other triangle has the same edge lengths, C and H, so Z squared is also equal to C squared plus H squared. And so now we have a value for all four of the edges. Now if we look at the triangle on the left, the length of W and X are given by the top two equations. We'll rearrange the second equation so that we can compare the two more easily. If we take the square root of both sides of each equation, that will give us the values of W and X. And hopefully you can see that W and X are not the same length, because the length of W is A squared plus H squared and the length of X is B squared plus H squared. But A and B are not the same length, because as we saw earlier, the perpendicular which passes through the vertex did not bisect the base. So the values of A and B inside these two equations are different, so W and X must be different. Assuming that the base is not the same length as W and X, this must be a scalene triangle, and we can see that the perpendicular that passes through the vertex, it is just a perpendicular line, not a perpendicular bisector. Now if we turn our attention to the large triangle on the right, it should be easy to see that the lengths of Y and Z are the same. because if we take the square roots of all parts of the equation, we end up with both y and z being equal to the value in the middle of the equation, so they must be the same length. And we know that the definition of a triangle with two lengths of the same side is an isosceles triangle, and they have the same length because the perpendicular which passes through the vertex of the triangle also bisects the base, resulting in two equal lengths, and this means that the lengths of the sides must be the same. What's going on essentially is that the horizontal position of the triangle vertex determines the length of the sides of the triangle, and if the vertex is exactly above the midpoint of the triangle, the perpendicular that passes through the vertex must also be positioned at the midpoint of the base, which means it bisects the base, and one of the results of that is that the edges of that triangle will be the same length, which is what we call an isosceles triangle. If on the other hand the vertex is not exactly above the midpoint in the triangle, the perpendicular that passes through the vertex does not bisect the base, and the result that we get is two different length sides. If you try this on all three sides of a scalene triangle, you'll get the same result. The perpendicular line passing through the vertex is not a bisector, but if you do this on an isosceles triangle that's sitting on its base, a line perpendicular to the base that passes through the vertex of the triangle will be a perpendicular bisector. In a couple of future videos, I'll be using this property as a foundation for proofs of other properties on other shapes. That's it for now. Thanks for watching.